All right, let's talk about AI memory. We see it everywhere, right? The AI that predicts your next word or the one that translates languages in a split second. But have you ever stopped to wonder how it actually remembers the beginning of a sentence by the time it gets to the end? Well, today we're pulling back the curtain on the really clever tech that finally gave AI a proper memory.
But first, let's start with the big problem. You've probably seen this yourself. Maybe a chatbot that totally loses the thread of your conversation, or a translation app that just butchers the meaning of a long sentence. Well, it all boils down to this one central question. Why can AI be so darn forgetful? It's a memory problem, plain and simple.
So the first real crack at solving this was a design called a recurrent neural network, or an RNN. The main idea here was actually pretty brilliant. Create loops in the network. This would allow information from one step to, stick around and influence the next step. It was built specifically for things that come in a sequence, like the words I'm saying right now.
But, and this is a huge but, there was a major catch. While these RNNs were good at remembering stuff that just happened, they were terrible with what we call long-term dependencies. The important info from the beginning of a sequence would just fade away as new stuff came in. It's a problem called the vanishing gradient. Basically, by the time the network got to the end of a long paragraph, it had completely forgotten what was said in the first sentence. Not great.
So, in this explainer, we're going to break down exactly how this was fixed. First, we'll quickly revisit that forgetfulness problem. Then, we'll get into the core solution, a kind of memory conveyor belt, and meet the three gatekeepers that run the whole show. After that, we'll check out some even smarter and faster variations. And finally, we'll see why any of this actually matters to you.
So, how do you fix an AI's terrible memory? Turns out, you don't just give it a bigger memory. You have to give it a smarter one. And that's where the hero of our story comes in, the long short-term memory network, or as everyone calls it, the LSTM.
Now, this wasn't some overnight success story. LSTMs were actually invented way back in 1997 by Hochreiter and Schmidhuber. Their idea was revolutionary, but it took a long time for computers to get powerful enough to really use it. Then, much later, in 2014, a leaner, meaner version called the GRU showed up. And today, these core ideas are absolutely fundamental to the AI we use every day.
Okay, let's get into the big idea that makes these LSTMs work so well. And you don't need to worry about the complex math. Instead, just picture a factory. Because the key to all of this is a simple but powerful analogy, a memory conveyor belt. The LSTM's secret weapon is something called the cell state. You can think of this as a special, separate pathway that runs right through the entire network. It's like an express lane, a conveyor belt that carries important information from the very start of a sequence all the way to the end, without getting messed up along the way.
So what's the point of this conveyor belt? Well, its job is simple, but absolutely critical. It preserves the context. By keeping this long-term memory separate from all the short-term calculations, it makes sure that a key detail from the first sentence is still remembered 10 sentences later. It just lets that crucial info flow smoothly.
Of course, a conveyor belt that just carries everything forever wouldn't be very helpful. You need a way to put new things on it, take old things off, and decide what to look at. And that is where the next piece of genius comes in, the three gatekeepers. LSTMs use three special gates to carefully manage what's on that memory conveyor belt. First up is the forget gate. It looks at the old information and decides what's not needed anymore. Like forgetting the old subject of a sentence once a new one is introduced. Next, the input gate decides what new, important information should be added to the belt. And finally, the output gate decides what specific piece of memory is actually useful for whatever the network needs to do right now.
And how these gates work is actually pretty straightforward. Each one is basically a filter. It uses a little bit of math to produce a number between 0 and 1. You can just think of it like a valve. If it outputs a 0, the gate is closed, block everything. If it outputs a 1, the gate is wide open, let it all through. This gives the network an incredibly fine-tuned way to learn what to remember and what to forget.
The LSTM was a massive leap forward, for sure, but the innovation didn't stop there. Researchers started wondering, hey, can we get this same power but with a simpler, more efficient design? And that led to some really clever new variations.
And that brings us to the Gated Recurrent Unit, or GRU. The whole point of the GRU was to take the best ideas from the LSTM and just streamline them. It combined the forget and input gates into one single update gate, and it got rid of that separate conveyor belt, merging it all into the main information flow. The result? A much simpler and faster model.
So, which one's better? Well, it's a classic trade-off, isn't it? LSTMs have more knobs and dials to tune, which means they can sometimes be a little more powerful on really big, complex datasets. But GRUs with their simpler setup are way faster to train and often work just as well, especially when speed is what you really care about.
Okay, so time for another twist. Both LSTMs and GRUs have one little limitation. They process information in only one direction, from the beginning to the end. But what happens in situations where you actually need to know the end of a sentence to make sense of the beginning?
Let me give you a perfect example. Imagine a sentence that starts, "He said, Teddy." Right now, at this exact moment, what is this sentence about? A teddy bear? Or maybe a president?
You have no idea, right? The word that gives Teddy its meaning, like Roosevelt or bear, comes later. A standard forward-only network would have to take a wild guess here. It just can't look ahead to see what's coming down the pipe.
The solution to this is just as elegant as the problem. It's called a bidirectional RNN. The architecture is simple. You just run two separate RNNs. One of them reads the sentence from start to finish, and the other reads it from finish to start. Then you just combine what they both learned. By doing that, the AI gets the full picture, the past and the future, for every single word in the sentence.
So we've gone through all these cool ideas, conveyor belts, gates, looking backwards and forwards, but why does any of this actually matter? Well, because this technology is quietly running some of the most amazing AI features that we all use all the time. These architectures are just incredibly flexible. For instance, when an AI looks at one single image and writes a whole caption for it, that's a one-to-many setup. When it analyzes years of sales data to make one forecast, that's many-to-one. And you know your phone's autocomplete that predicts the next word based on what you just typed? That's a classic many-to-many problem. Even analyzing video and classifying objects in every single frame uses these exact same principles.
So here's the bottom line. The huge challenge of AI forgetfulness wasn't solved by just giving it a bigger memory bank. It was solved by giving it a smarter one. LSTMs, GRUs, and all their variations gave AI a dynamic, flexible system to selectively remember, forget, and update what it knows over time.
So when we boil it all down, it really comes back to three key breakthroughs. First, that cell state, the memory conveyor belt that keeps contacts safe. Second, the gates, the intelligent controllers that manage that memory. And third, bidirectional processing, the power to look both forwards and backwards to understand the whole story.
This ability to understand sequences and context has been absolutely revolutionary. It really is the foundation for so much of what we think of as AI today. And that kind of leaves us with one last big question to chew on. Now that AI can effectively remember the past and predict the future, what's the next great cognitive barrier for it to break through?